Alright, so guys, we're talking about formation of the Earth today. And this is what we're going to be talking about today. Where does the Earth really come from? Where did the moon come from? And that's kind of what we're going to be looking at today. So we have a couple activities. This is going to be a 2-day lesson. So today we're mostly going to be talking about where the Earth came from. Tomorrow we'll kind of finish up where the moon came from. But basically, we're going to start from the beginning of time and go forward. So, when we look at the beginning of time, we start off with this thing called the Big Bang Theory. And it's a whole bunch more than just a show. It's a great show. So, can you guys tell me what you know about the Big Bang Theory? Not in terms of the show, but rather in terms of the actual scientific theory of the Big Bang. Okay, go ahead, Dan.
I guess it's supposed to be that everything came so close together that it got so tight or something that it exploded and then there was a universe or something like that.
Alright, so basically all the matter in the universe is wrapped into a very small space, and then there's an explosion of energy, everything gets spewed out. What is the... I mean, that's kind of... almost sounds like that's how would you put that? Almost sounds like a crackpot idea, right? I mean, it's really out there. But, what is the evidence that scientists have that suggests that is possible? Matt?
Because when they're using their big fancy telescopes, they can see that the I think it's called the universe, right?
Yeah, universe.
Okay. I look at those stuff. The universe is keeping on expanding.
There we go. Sorry, we have an expanding universe. Okay. Now that big fancy telescope that they use is called a spectroscope. And what a spectroscope does is it looks at the EMR spectrum. EMR meaning electromagnetic radiation. Okay. All light travels as both the waves and packets of energy. Those packets of energy are called photons. Sometimes it acts as particles, sometimes it acts as a wave. We really don't know why. We can't really separate one from the other. But when we look at the EMR, we go all the way from alpha waves to radio waves. Now, that's kind of important. I mean, we're going from really short wavelengths to very long wavelengths. Okay, and that's your EMR. And that's basically what it means, electromagnetic radiation. When we look at light, in terms of what we actually see in terms of color, light is actually just a very small fraction of the entire EMR. Okay, so our view is actually very limited. So not only are we only here for a very short while, we also have a very limited way of looking at things. But oddly enough, it's actually as our bodies are built to optimize our view of the EMR. Now there are other animals that can sense the other pieces of the EMR. We just aren't one of them. But anyways, so we look at a spectroscope, and we have these things called a blue shift and a red shift. Blue shift, well, if you look at a blue wavelength, it's a very long wavelength. When you look at reds, they have very short wavelengths. Suppose I had a slinky. We'll check it. Suppose I had it. Dan and I are sitting up here facing each other. He has one end of the slinky, I have the other, and he starts walking away from me. What happens to the wavelength of the slinky? So it expands. It's stretching out, right? Because he's moving away. What if he's moving toward me? Yeah, it's compressing the wavelength, so we get smaller waves. Okay? So if things are moving toward us, we get a red view to them because it's compressing that wavelength. If things are moving away from us, it's blue because it's stretching out the wavelength. Okay? Now that light being returned back and forth. It's the same way the Doppler works. You ever wonder why we have green dots and red dots on the Doppler radar? Okay? It's not because that's rain and that's not. The green is actually technically it's supposed to be a blue, but it's basically showing the red means it's coming towards you, blue means it's moving away from you. And that's how they actually can see things moving in and out. That's how they identify the spiral. And that's really what, when they talk about the storm tracker, and they found these thunderstorms, that's actually the whole thing, all they're doing the whole day with that thunderstorm is watching for rotation within that thunderstorm zone. That's usually this concept of the spectroscope. So blue stretches out the wavelength that's moving away. Red compresses as it's coming in towards you. When we look at the universe, no matter where we look off our little planet, everything's blue. What does that mean? It's expanding. Everything's moving away from us. Does that mean that we're the center of the universe? Well, we used to think so. But we're actually not the center of the universe. I want you to envision a bomb. Yes, I said bomb in school. Okay? Just don't say that in the airport. Alright, so we're into the bomb. Then it goes boom. Yep. Except the one that does. So, let's go boom. Envision yourself as being a particle. You split out from the bomb. You yourself are moving away from the center of the bomb, correct? Well, when you actually stop, let's say you just take a stop, and so we're able to freeze everything, and you look around you. What do you notice about all the other particles relative to you? What do they do? They're also moving away from you, right? Alright? So when we actually are talking about the Big Bang Theory, this is actually the evidence we're looking at. And everywhere we look, everything's moving away. And what we've done is we can actually sit there and say, okay, well, what if we put that in reverse? We back it all up. And that's how we actually get to this theory that the Big Bang starts with a single speck. All the matter and mass of the entire universe is put into a space about the size of the top of your pen. And then it's released a lot of energy. Okay, so that's really the Big Bang Theory, if you believe it. If you believe that there's more than 6,000 years old. Yes.
I was going to ask you about that. Wasn't there a timeline out there for this complex and stuff?
I was actually just talking with them. Since on our scale, 1 centimeter is relative to 1 million years. So that means that 1 millimeter is 10,000 years. Which means that, oh, no, that's not right. 1 millimeter would be 10,000. That would be, yeah, 10,000. Okay. So that would be that all of the animal existence, 6,000 years, is half a millimeter.
You could change the scale.
We don't have that much room. I get all that for taking up both sides of the hallway.
What else are they going to do?
How long that can be up there?
What else are they gonna do?
I realize it was an eyesore, like what's downstairs in the hallways. Sorry. Maybe you can watch your kids